Thanks, Wanderlei, and thanks for all the organizers, Cardinal Turkson, Professor Joachim von Braun, Bill, and Wanderlei for inviting me and us to this wonderful workshop in the most special location I've been. I will tell you about strongly interacting quantum gases. There will be fermionic gases, bosons, microscopes, and I hope it will be an enjoyable 20 minutes. The motivation for this is to basically understand what holds things together. It turns out I'm particularly fascinated by fermions, and it turns out every massive elementary particle happens to be a fermion, those guys that don't want to be in one quantum state. So you have, of course, complicated things like nuclei, very small things, or very large things like neutron stars, far away, hard to touch, very difficult to understand. And even on a human scale, you have these high-temperature superconductors or other strongly correlated electronic systems that are very difficult to grasp because we do not have a general theory that solves fermionic problems. It gets even worse once you think about dynamics of fermions. So think about modeling nuclear fission ab initio, absolutely impossible. In the high-TC context, we invent names like strange metals because we don't understand what they are. And I bet if you have seen these neutron star merger events from LIGO, your imagination must go wild as to how these Fermi systems merge and rub against each other in some gigantic collapse. So how do we get to a strongly correlated matter? I list two routes, probably infinity. But one is if you're so lucky to already have strong interactions in your system, you're good to go. So with cold atoms, that happens when you use the magic of Feshbach resonance, the bound molecular state, to induce strong interactions. But we have heard yesterday in wonderful talks by Randy and Emmanuel that you can also quench the kinetic energy and thereby bring up the role of the interaction energy by switching on an optical lattice. Or what I will also mention, the possibility to dress the energy levels in such a way that they become flat. And that happens, for example, in twisted bilayer graphene or the quantum Hall physics. So as the first topic, I want to introduce you to a strongly interacting Fermi gas of two spin states, spin up, spin down, or here blue and red, with tunable interactions between them. So that allows you to sweep from a Bose-Einstein condensate of tightly bound molecules, these are now bosons and therefore want to form a condensate, to the long-range Bardeen-Cooper-Schrieffer Cooper pairs of the BCS state. And it's actually smooth crossover going through a special regime, the crossover superfluid. If you ask what temperature do you have to reach to see this, well, it's the degeneracy temperature of bosons in the case of tightly bound molecules, but it's the very fragile temperature of the binding energy of these fermion pairs in the BCS regime. The pairs become very fluffy and fragile, so you have to cool very much. Conventional superconductors are far on the right side of this graph at a temperature that's 10 to minus 5 or 10 to minus 4 of the Fermi temperature. High-TC superconductors are at 1% roughly of the Fermi temperature. And the high-TC superfluids we can create in the lab are at 20% of the Fermi temperature. So we say sometimes scale to the density of electrons in a solid, you would get superconductivity far above room temperature. Turns out also far above the melting temperature of most things. So almost 20 years ago now, wow, we have demonstrated superfluidity in these strongly interacting Fermi gases by rotating the gases and observing lattices of quantized vortices piercing through these clouds. Especially interesting is the point of the strongest interaction that quantum mechanics allows right at the Feshbach resonance. Now you no longer have an interaction-dependent length scale, and so the only length scales that matter are the distance between the particles and the de Broglie wavelength. So it's a very universal gas described by only two energy scales, the Fermi energy and the temperature. So that gives you a universal equation of state that if you scale it to the density of a neutron star, actually matters for the equation of state of those faraway objects. The ground state energy must be some number times the ground state energy of a non-ejecting Fermi gas, and we measured that number to be 37%. The attraction between fermions makes it a bit lower energy than a non-ejecting Fermi gas. The critical temperature is 17% of the Fermi temperature. So it's a high temperature superfluid, even though, of course, in our lab, it works at nanokelvin. 10 years ago, we did what you could call a Feynman quantum simulation. So you throw your fermions in your trap, and now you do what the hiker does on a way to the mountaintop. The hiker picks up the density as she climbs up, and picks up the density as a function of height. And so the derivative gives you the compressibility, and the weight of the air column above you, that's the pressure. So by just walking up the hill, you can actually obtain the equation of state of this strongly interacting Fermi gas. And the red data points are the experiment, and the other scattered points are various theories for the strongly interacting Fermi gas that were available at the time. And in particular, so it's interesting that the experiment has small enough error bars to distinguish certain theories. And also interesting is to see the blue data points with error bars from a newly developed theory that is sampling the series of Feynman diagrams, and that seems to work spectacularly well within the error bars. They're still working on the superfluid regime as of now, as I heard here. So there was actually an interesting blog post by John Preskill at the time, who asked, "Supremacy now?" I think that would be a nice topic for discussion later. But whether supreme or not, it is useful, because in fact the unitary Fermi gas constrains neutron matter. So this here is the equation of state of neutron matter, as according to various theories, energy per neutron and number density. And if you look at this dot dashed line, that is actually the unitary Fermi gas. So an ultra-cooled Fermi gas, 1,000,000 times thinner than air, constrains neutron matter at 25 orders of magnitude higher densities. That's why we love physics. It only matters what the relative scales are. Really difficult is when you get to transport. So I can give you in short amount of time an idea of what the typical diffusivity of such a gas. It is quite amazing. The mean free path is just one interparticle spacing. So that means whenever the atoms encounter each other, they scatter. De Broglie tells us now that that means that the average velocity of this gas will be related to Planck's constant, the particle mass, and also this interparticle spacing. And once you multiply the two to obtain a diffusivity, you realize the interparticle spacing drops out, and you get a universal diffusion constant, or actually a scale of diffusivity that is given just by Planck's constant and the particle mass. And that will be true for the unitary Fermi gas at low temperatures, whether you think about charge or the density diffusivity, spin, momentum, or thermal diffusivities. So I will quickly tell you about two things we measured recently. We put our gas in a box, not a box with real walls like this room, but the box is made out of light. And the atoms spend most of the time in the dark and only sometimes encounter the light when they bounce against the walls. And then we excite sound pretty much like in the pool on the left side. Of course, our scales are much smaller. We are talking about 100 microns and not these wonderful 20 meters. I would love to have a 20-meter sized pool of fermions. And when you do this, you do an undergraduate experiment where you see the sound wave get excited and then damp out towards the right. And so as a function of space or time, you can measure how the sound wave gets damped and extract the sound diffusivity. And indeed, it is on the order of h bar over m at low temperatures. The red line, the vertical line, shows actually where the superfluid transition happens. So nothing special happens at superfluidity. Well, what is special about a superfluid is that there are two fluids to think about. There's the superfluid and the fluid of excitation, the normal fluid. And so you get two sound modes. Famously, that was predicted and observed in helium, predicted by Tisha and Landau, and observed for the unitary Fermi gas by Rudi Grimm in collaboration with Sandro Stringari, who's in the audience, and Lev Pitayevsky in 2013. We have measured directly the heat in this system. So we used an atomic physics spectroscopic probe to measure heat in this system, just making use of the fact that the radio frequency spectra of these gases depend on temperature. So you can sit at one frequency and immediately know how hot the local spot is that you're looking at. And with this, you can actually see heat sloshing back and forth in your system. Second sound, the propagation of heat, second sound. And as you tune through the superfluid transition temperature, it can go from a normal fluid at high temperatures where heat just diffuses exponentially, boringly, to a superfluid regime where you see heat sloshing back and forth like second sound. So that's a quite remarkable way to see the superfluid transition. Now, if you compare to other Fermi superfluids, we can actually look at this plot. It's called the Uemura plot, which plots the critical temperature on the y-axis against the Fermi temperature on the x-axis. And the cold atoms are in the middle only because someone scaled both axes by 10 to the 8. Otherwise, you wouldn't be on this plot. But what is important, we are the closest to this kind of diagonal line, which is the critical temperature of a Bose-Einstein condensate boson. And so that, again, gives hope that, you know, in principle, there's no reason why there should not be one day a room temperature superconductor at ambient pressure. Don't ask me how to make one, though. So now the question is, if you're not so lucky and you don't have interactions that are strong, can you still induce strong interactions? Yes, let's put the gas into an optical lattice, and we have already heard that the Fermi-Hubbard model is a very interesting system to study. It starts with a cold atom proposal by Misha Lukin and Eugene Demler and colleagues in 2002. And then there was a myriad of activities, lots of papers trying to understand better and better the system. We heard about the beautiful measurements by Randy on the antiferromagnetic correlations yesterday. And the breakthrough came already for bosons in 2009 and 10 by Markus Greiner and Emmanuel Bloch's groups with Wasim Baker and Stefan Kur leading the experiments to obtain Bose gas microscopes. And in 2015, we and other groups implemented this for Fermi gases. And this gives now a microscopic view of these fermions and their pairing. I will tell you about the most qubit, ask me later about it, but I will tell you about the direct observation of fermion pairing under the microscope. Surprisingly, this Fermi-Hubbard model, the moment you switch on attraction, is again showing you a beautiful BEC-BCS crossover, so you don't have to relearn things. It is BEC-BCS crossover. There's some subtleties. In particular, what's prominent here is that above the critical temperature of superfluidity, like in the bulk, you already have pairs without them being a superfluid condensate of pairs. So you have preformed pairs. So those are the ones we are after. And by the way, if you think that attractive Hubbard model is sort of remote from the high TC superconductors, it's actually directly mappable to the repulsive Hubbard model. I don't have time to go into detail, but there's a beautiful particle hole mapping between the two, mapping the antiferromagnetic, for example, to a charge density wave. So here are the pictures from this microscope where you see spin up and spin down fermions under the microscope, first without interactions, and then as you switch on the interactions, you see more and more of the white dots. The white dots are W-occupied sites where spin up and spin down are on top of each other. And if you squint your eyes, it's not so hard to see that there's already some sort of pattern forming among those white dots. So they start to form a charge density wave for these strong interactions. So this is a close-up picture of one of these gases where I already pointed out charge density wave correlations. And also you see these red and blue dots here and there. Are they random? They seem to be occurring very close to each other. Is this by accident or not? Well, if you repeat 100 shots, you realize, no, they're always next to each other. Whenever there's a spin-up atom, there is a spin-down atom nearby coming from a fluctuation of one of these doublons into neighboring spin-up, spin-down pairs. This is for weaker interactions. You don't know what's going on. It's just sprinkled with blue and red and white dots. But again, if you take statistics, you can demonstrate that these are fully paired gas, even though the pairs are non-local. So this is very much in the spirit of Cooper pairing. And so as a cartoon picture, I try to connect, marry which spin up is married to which spin down. This is, of course, just a cartoon picture. Most importantly, we can measure these correlations and the length of the correlations and see that they're much longer ranged and then the interparticle spacing. So this gives us an idea of the phases of the Fermi-Hubbard model at the temperatures we can reach right now, from the molecular gas on the left-hand side for strongly attractive interactions to the Mott insulator and band insulator for strong repulsive interactions on the right-hand side. And as I mentioned, this is a beautiful mapped phase diagram between the left and the right side, between attraction and repulsion. And the spin pair fluctuations I've shown you so far are directly related to Dablon-Ho fluctuations on the repulsive side. Brings me to the final part. What about dressing the energy levels to be flat, to become flat, to get into Landau level? To do that in cold atoms, the very first way was taught to us by Jean Dalibard, who's also in the audience, showing us dramatically the first quantized vortices in Bose-Einstein condensates, a dramatic demonstration of their superfluidity. And of course, people started rotating faster and faster, and Jean and his group managed to get to the lowest Landau level, basically seeing that the vortex lattice is melting, and experiments like that were also done by Eric Cornell in beautiful ways, looking at this vortex lattice and its fate as you spin it up faster and faster. But it seemed to be sort of a difficult direction, because as you spin up very fast, the centrifugal force everyone feared would just destroy your gas, and that would be the end of it. So beautiful, different ways of designing artificial magnetic fields were devised. They all had some difficulties putting in the interactions into the picture. So that's why we actually went back, basically 20 years later, to rotate gases. And the recent progress has been that we have found a new way to get into the lowest Landau level by geometric squeezing. We can watch these Landau gauge states decay into crystalline states, and we also observed chiral edge states in these systems. So I'll try to walk you through. I should start with the first experiment that demonstrated non-commutative geometry on Earth. That was Foucault's pendulum. And we all love how the plane of the pendulum swing precesses as we watch closely. If we were to spin up the Earth to dramatic speeds, dramatic rotation speeds, you would see funny behavior of this Foucault pendulum. It would actually look like the pendulum is crawling around the edge of your Pantheon or wherever you hang it, which is a good occasion for me to introduce the guiding center and the cyclotron coordinates, just like in an undergraduate lecture. The guiding center ones are the slow oscillator. It's the magnetron mode for ion trappers. The cyclotron motion is the fast oscillator. So if you're cold enough and you rotate near the trapping frequency, near the pendulum frequency, you're in the lowest Landau level. So this happens, you can easily quantize this problem. Here you have a quantum Foucault pendulum. You see it's a blob now, not a point, because Heisenberg limits the size of this blob to what we call the magnetic length, which is just given by the harmonic oscillator length correlated to the cyclotron motion. And on the right-hand side, you see the quantum energy levels. As you rotate up to the frequency of the trap, you get into the Landau level. So life in this lowest Landau level is bizarre. There's a vast degeneracy of states. They all have this size of the ground state energy, of the ground state size of this harmonic oscillator. And of course, if you now apply a potential that varies slowly compared to the size, it cannot resolve the cyclotron motion. So it's a potential that acts within non-commutative space. Slow down, because that is the essence of quantum Hall physics. And if you now think about applying a transverse gradient, for example, apply a force along x counterintuitively, the atoms will instead escape sideways, drift sideways, which is just nothing else than the E cross B drift that you know from electrodynamics. So this is, of course, sweeping many details under the rug, like localization, etc., the essence behind the quantum Hall effect observed by von Klitzing, who is in the audience, which is amazing. And so now let's see what happens to bosons. What we just saw was with electrons, which are fermions, and now this is now an experiment on bosons. It takes a few seconds to build. And the special thing about this experiment 20 years later is that we can actually see vortices under the microscope without any expansion. So we have the resolution to see quantized vortices in situ. So let's stir up our trap. like Jean did in the olden times. It still works. And go directly to the rotation frequency, which rotates at the underlying isotropic trap. Then the remaining potential happens to be a saddle potential. You're a little bit tighter in the x direction, a little bit softer in the y direction, so you get an x squared minus y squared potential. Let's see what happens. So in the lab frame on the left-hand side, well, condensate starts rotating, spinning up, and it becomes very elongated, and it thins out as well. And the rotating frame is a bit more pleasing to see and watch. The condensate stretches out, thins out. What is happening? This is actually nothing else than a gauge transformation from the symmetric gauge to the Landau gauge that we learned in undergraduate quantum mechanics. For the quantum opticians among us, we had a wonderful talk by Martin Scully yesterday. The x squared minus y squared is just a squeezing Hamiltonian. So now what is the fate of these Landau gauge condensates under the influence of interactions? It turns out they break up. There's a snake instability, and you get this rather beautiful array of droplets where each droplet is rotating about its own axis. So we can understand this is actually nothing else than what we heard yesterday, pair production, K minus K modes being spontaneously excited in this lowest Landau level. And if you put K minus K together with a non-moving condensate, you get a snake. It's very simple to write down. And you can also directly do the math and see, yes, it's an unstable system. But very surprisingly, there is also a classical interpretation for very large systems, for very thick systems that occupy many Landau levels, and that is the old wonderful story of Kelvin-Helmholtz instabilities of counterflowing liquids. So it's the same thing that you sometimes see in the sky if you're lucky, and it's quite beautiful how this quantum instability is directly connected to a classical instability. This is a wonderful picture of what happens on Earth in atmospheric waves. It's basically the same phenomenon on our good Earth, which is a wonderful non-commutative space. You can extend this to two-dimensional structures where you see weird effects, galaxy formation, and so on. It's beautiful to look at. We can talk about it later. I already showed you the chiral edge states that propagate at the walls of our system. If you write some walls, and this is also a fascinating direction, these are protected. So if I put an obstacle in there, the edge state crawls around it without backscattering. As an outlook, we have to combine vortex and atom microscopes to get to beyond mean field quantum Hall state, where bosons might also undergo the fractional quantum Hall state through interaction. So we need to have as many atoms as vortices, or as few atoms as vortices, and that will require atom microscope. So with that outlook, I thank you for your attention.